Good afternoon. My name is Eka Sinerva, and I have the pleasure of being a professor of physics here at the University of Toronto. And I have, in fact, the greater pleasure of introducing to you Professor Tony Nobel, who's a professor of physics at Queen's University and a Canadian research chair in particle astrophysics. When I pulled out the piece of paper that I was going to read to you, Tony's reaction was that I was going to actually be talking to you about his abstract for his doctoral dissertation, given the length. I'm not going to read everything I wrote down. There's far too much to say about what Tony has done to particle physics and astrophysics in Canada, much more than I could actually even begin to give you a real taste of. Tony actually started his career here in Canada. He did his doctorate at UBC. He was actually working on trying to understand how particles that are called lambda particles, essentially protons, but with a strange quark inside them. He was trying to understand how they decay. And they decay because the strange quark itself decays. But it was an interesting thing to look at because it was an interplay between the forces that hold quarks together and then those that cause them to decay, the strong and the weak force. So we did a precision measurement of one of the properties of the lambda particle for his dissertation. This gives you a sense that, in fact, what he does is look for interesting problems and then do the best job possible experimentally to actually crack the problem. He did that, then subsequently he went on and studied proton, antiproton annihilations, where you bring a proton and antiproton together, and in the burst of energy, you produce new types of particles. And so by doing that, you could actually explore, what we actually started calling a particle zoo in elementary particle physics, where there were so many particles that we were discovering, so many types of particles, it actually became hard to see what the patterns were. The work that Tony did after his doctorate was really focused around figuring out what those patterns are. And those were the sorts of studies that he did. He was then naturally drawn to an experiment taking place in Sudbury back in the late 1990s called the Sudbury Neutrino Observatory, or as we call it, SNO. The SNO was 2 kilometers underground, designed to actually try to crack what we called the solar neutrino problem. And at the time, that was a problem that when we looked at the sun, we actually saw, to the extent we can see, that there were not enough neutrinos coming from the sun. And you're going to hear about that from Tony. They built a detector underground that could actually count the number of neutrinos coming from the sun and see whether, in fact, our idea of how the sun worked was wrong or our ideas about neutrinos were wrong. As it turns out, Tony joined the experiment as they were finishing construction of the device underground. He became responsible for the $300 million heavy water, plant underground that was used as a target for the neutrinos. He was actually the associate director of the project when the team published its first paper in 2002 that demonstrated conclusively that, yes, the sun was just okay, still was working right, and the fact was that neutrinos behave in a way that we never would have thought possible. That became the most highly cited paper in 2002 in the world, and ultimately then led to the Nobel Prize being awarded to Art McDonald in 2015. Of course, there was another Nobel involved in that, Tony. And so Tony, after having worked on SNO, then became involved in building SNO Lab, which became a laboratory that, in fact, enlarged the area that the SNO experiment was in. As head of that effort, it was about a $50 million project to expand the laboratory. He took a leadership role in that, was head of essentially the institute at Queen's that oversaw that project. And today that laboratory is one of the world's internationally significant underground laboratories. And you'll hear a fair bit about that from Tony in his talk. Finally, in 2018, Tony took a leadership role and founded the McDonald Institute. This was a large institute that was set up to actually build out and strengthen particle astrophysics in Canada. Since it was established, the McDonald Institute has created 15 faculty positions in particle astrophysics across Canada. There is no other effort I can think of that actually has added 15 research faculty in a given field in this country. Yet Tony has actually been at the head of that, made it work, and in fact was critical for, in fact, the renewal of the funding of the McDonald Institute that was announced just in the last year. As you can tell, Tony is one of those sorts of people that is unassuming when you actually meet him, but in fact is his impact in our country goes way beyond that particular persona. So please join me in welcoming Tony.
Okay, thank you. So as warned, I'm going to be talking about neutrinos today. And I know a lot of people don't know a lot about neutrinos. So when I start, I'll introduce a little bit about first neutrinos, but also the field astroparticle physics, which is also probably a new term for some of you. I was at a conference recently at Waterloo, and there was a poster there, two posters. One had Art McDonald's face on it. The other one had Donna Strickland. And there were tons of undergraduate students from Waterloo attending this conference. I asked them who they were. Nobody knew. And so I thought for this talk, I was going to go back and explain a little bit about the Snow legacy, what was discovered, how it was discovered, but then move on to the second half and show you how the field has advanced since those early discoveries. And so I have a number of sort of case studies of what we're doing now. So I come to this, as Pekka mentioned, with a background in particle physics. But astroparticle physics brings together all of these things. So I'm interested, there's tons and tons of fundamental physics that you might be interested in. That's my particular interest. But those particles are also produced out in the cosmos, supernova explosions, black hole mergers, active galactic nuclei, sorry. And so there are people who are more focused on the astronomy who are looking at those sources and trying to learn what's happening at those sources by using the particles that are coming to Earth. So that's why it's astroparticle physics. And once you know the basic building blocks and how they work, and then you have some idea of what the content of the universe is through astronomy, then that leads you into the field of cosmology, where now you can use those building blocks and the sources and all the objects to understand how the universe came to be, how it will evolve, and so on. And so that's the realm of cosmology. Okay, so let's get into it with neutrinos. So I start very basic here. This will be too basic for many of you, but if neutrino beer exists, and so if you buy a can of neutrino beer, but then you look inside, what do you see? Why is that not working? Well, I picked this is mostly water, right? And that's because this is an American beer. But it's true. There's a lot of water in beer, and everybody knows that water is a molecule, H2O. Okay, you don't have to believe that. And so, but if you then think about the oxygen, what is the oxygen? Okay, it's an atom surrounded by electrons. And generally speaking, oops, I'll get used to this, buttons. Okay, so this atom was thought to be indivisible for a long time. That was the basic building block of nature. And it was indivisible. And so for a long time, people worked with that hypothesis. But then as accelerators got bigger and more energetic and could probe more inside these nuclei, we discovered that it was actually made of neutrons and protons. Okay, but clearly they were indivisible, as the theme goes. And a lot of physics, of course, was done. Now you can understand all the different isotopes. that are made. You don't just have carbon, you have carbon 12, carbon 13, carbon 14 by adding or subtracting neutrons and so on. Again, long thought to be indivisible until bigger accelerators were built that could probe even deeper and could now, by shooting things through here, recognize that you're bouncing off objects within the nucleus. And so were quarks discovered, right? And so in this simple model where I have a proton, a couple of up quarks and a down quark, the neutron, an up and two down, but very fundamental. These are what we consider now to be indivisible. You can take that with a grain of salt, but for 50 years now or so, we have not been able to find any structure inside the quarks. So maybe that's it. And when you put that together, you get what's called the standard model. And most people are fairly familiar with the standard model, I think, in that it has these 6 quarks here, which just basically come together to make things like protons and neutrons and heavy brothers and sisters of those things. The lambda, for example, by adding an S quark instead of just up and down quarks, as Becca mentioned, was my thesis topic. But you also have electrons. Everybody knows electrons, but there are bigger brothers to the electron, the muon and the tau particle, for example. Now, these guys are the fundamental ones that most of nature exists in because they're the lowest mass ones. You can produce these things by adding a lot of energy, having collisions in big accelerators and stuff. But eventually, they decay back down, and eventually it's very quickly, and you end up with just these particles. So as far as you're concerned, most of everything you see are made of these particles. But then there's these strange part of the family here. These are the neutrinos. They're just as fundamental as an electron or as one of the quarks. The problem is they're neutral, so they're very hard to see, and they interact incredibly rarely. So even though they were predicted back in the 1930s, because otherwise energy and angular momentum didn't work, it took 25 years or so to discover them. That was in the 1950s. And we're still doing experiments on them today because we still know very little about these neutrinos. The other things in this picture are we have forces. My hand doesn't go through this table because the electromagnetic force is stopping it. And they are basically, these are the propagators of the force, the particles that allow forces to happen. And then you've probably heard about the Higgs boson. There are people here associated with that measurement that discovered the Higgs, which is what allows the particles to have mass. But the things I'm most worried about are these particles over here, which are the fundamental building blocks, and in particular, the neutrinos. Now, one little twist to the story is that for every one of those particles, there's actually an antiparticle. So we've got to remember that. And in my postdoc work, in fact, we took protons and collided them with antiprotons. So you had to make the antiprotons in a big accelerator, making collisions to make those things. But that was something we could do. And when you do that, you just get energy out. And now you can make anything. And so you can make all kinds of exotic particles by just taking an antiparticle and smashing it together with a particle. And they exist in nature. About 1 in 5,000 cosmic rays hitting the outside of our atmosphere is an antiproton rather than the proton. You are probably familiar with things like positron emission tomography, where we take positrons, the anti-electron, and use that to assay and monitor what's happening in people's brains, for example. Okay, so the odd thing, though, is we would imagine that these were all built at the beginning of, or created at the beginning of the universe. And so you would have equal amounts of matter and antimatter. But when we look to the universe, we see that it's just matter, essentially. Everything we see is evidence for matter. And so the thought is there's some asymmetry at the beginning of the universe, probably about 1 part in a billion, where you had 1,000,000,001 particles and only 1,000,000,000 antiparticles. And so all those billions have disappeared and left 1 over. And then everywhere that happened, we end up with just matter left over. understanding that is a high priority question in astroparticle physics because it's very difficult to build a model that explains exactly how this asymmetry could have come about. And we'll talk more about that as I go on. Okay, so what are the properties of neutrinos? I said they're fundamental particles. They're part of the standard model. What's important for this talk is that the only type that is made in the sun, because of energy considerations, is the electron type neutrino. So that's what's made in the sun, and only that one. Right? They have almost zero mass, so we know it's not zero, but it hasn't been measured yet, actually, but it's at least 1,000,000 times lighter than the electron. And so that should give you some sense of scale. It has no charge. That makes it really hard to see. They're extremely abundant. If you hold out your thumbnail, there's some tens of billions of neutrinos going right through your thumbnail every second. Tens of billions. And of course, a lot more going right through your entire body. And yet, in your lifetime, you have a chance that maybe one neutrino will actually interact in your body. The rest just blow right through you. Right? So that's what makes them very hard to study because they go through everything. That's where I said very weakly interacting. The sort of the figure of merit is that if you took a light year of lead and shone a beam of neutrinos of the sorts of energies we're looking at, then most of them would get through that light year of lead without ever having an interaction. Okay? So extremely weakly interacting. Okay, so I call them these wisps of near nothingness, and that's what I spent my life studying. Okay, so what was the solar neutrino problem? Pekka alluded to this, that we are trying to understand the neutrinos coming from the sun. And I'm not going to go through this at all in any detail, but you see that it's a very complicated sequence of reactions, fusion reactions in the sun that produce the heat, burn the hydrogen, the two protons. And every now and then you see it produces a neutrino, a neutrino, a neutrino, you know. The one we were interested in was this neutrino, way down at the end of this long, complicated chain with only, a hundredth of a % probability of getting there. But that's the neutrino we were studying. Why? Because it had a higher energy, and the higher energy had allowed us to detect it. Okay. So for 35 years, very sophisticated experiments were trying to understand how many neutrinos were coming from the sun. And what they discovered is shown in this plot. So these are all different experiments, started in the US, some experiments in Japan, in Russia, and Europe. And in all cases, the blue is how many neutrinos they saw, and the yellow, all of these normalized to 1, the yellow is what they expected. So every experiment saw far fewer neutrinos than expected. I don't know about you, but if that was the result I got, and I did this calculation of all the fusion reactions in the sun, all the complications with the helioseismology and everything that comes into it, and then knowing what happens when they get to the Earth, and I was only off by a factor of 2, I would say, wow, that's pretty good. Time to go home, right? But as time went on and the calculations got more and more refined, it seemed there was very little wiggle room to blame it on our understanding of the sun, but maybe there was something weird happening with neutrinos. So that's what we set out to do, was to look for those guys. Why is this thing not moving? Okay, so this is my sort of visualization of this. Here we are at the Earth. The expected flux of neutrinos is coming. There's 6 of them there. We only see roughly a third of them arrive at the Earth. So what is going on? So the snow detector was designed to build that. And working on snow, I have to say, was a real luxury. Not just because the collaboration was great and working with Art McDonald was great, but this was an experiment like you don't often get, where we knew that there were 2 possibilities here. Either the model for the sun was wrong, or the model for neutrinos was wrong. And if we did the measurement carefully enough, we would answer that question. And it was one of the biggest questions in science of the day. And it's not often you start an experiment knowing if you do it right, you're going to make a major discovery. But it was hard. First of all, on the surface here, we are all being rained down upon by cosmic rays. And so that just wouldn't work. You're looking for something that is so rare, only a couple neutrinos a day, and yet we're in this bath of cosmic rays, which are hitting us all the time on the surface. So to get rid of those, you go 2 kilometers underground, and that 2 kilometers of rock filters out most of these things. Not all of them, but down to a very manageable level. And the advantage of Snow Lab is that it's actually one of the deepest labs in the world. So if you were to go to Snow Lab and visit, you would go down 2 kilometers on what's called the cage, it's the elevator, and then you'd walk another 1.5 kilometers till you get to the snow site. Way out here, because actually there's mining happening there. We didn't want our lab to be in the middle of a dynamite blasting field and so on. So we punched through here and created snow. Whenever we saw some nickel, we kind of kicked it aside so the miners wouldn't see it and know that this was an interesting place. So that's what we built. The detector itself was a huge undertaking. It went in this cavern that's the size of a 10-story building underground. That was the biggest cavern that had ever been built. And we really had to work with industry and the mining technology to figure out how to make that safe and supported. But basically, it's a big ball of heavy water. So the deuterium here is the heavy water. It's a deuteron. It's just like hydrogen, so H2O, except it has 1 extra neutron attached, which chemically, the chemistry is driven by the electron. So chemically, it's not so different, but it's much more massive. And there's a reason for it, which I'll get to in a second. So that was the idea. And then, of course, if a neutrino comes in, it hits something, 1 in some billionths of a time. It makes a little flash of light. And so on the outside of this, we had 10,000 light sensors all the way around. Now, that elevator that brought stuff down is about this wide and maybe a little bit longer. Everything had to be built like a ship in a bottle because you couldn't bring any big piece of equipment down. And so there's something like 300 panels here, all glued together underground, hopefully in a way that it doesn't break, because as Pekka said, I was responsible for the $300 million worth of heavy water, which we were able to borrow for $1, as long as we gave it back. And the dollar really did change hands, I'm told. Yeah, and this was really a Canadian experiment in many ways. Of course, it was led by a lot of the scientists in Canada, but also heavy water is what we use in CANDU reactors. So Canada had the biggest supply of fire. They had tons and, thousands of tons of heavy water. Whereas at the time we started, the entire inventory in the US was something like 30 kilograms or something, just because there's no other real need for it other than the CANDU reactors. Okay, so why did that change? So there are 2 basic reactions I want to take you through, because this is the nuts and bolts of how snow was successful. Because of this deuterium, right? So I told you that's a neutron and a proton. That's my deuterium. So in one reaction, a neutrino comes in and it hits that thing and it turns a neutron into a proton and kicks out an electron. So your job is to measure that electron. If you see an electron flying through your detector, then you say, aha, this reaction happened. I now know how many electron neutrinos were produced in the sun. Okay? That's also what all the other experiments were able to measure, how many electron-type neutrinos there are. What made snow different and why we use deuterium is that there's another reaction, which is if any old neutrino, it doesn't matter if it's an electron, a tau, muon-type neutrino, it just has enough energy to hit the deuteron and break it into 2 pieces. And so in that case, it comes in, it hits this thing, and it breaks it up into a neutron and a proton, and the neutrino just bounces off and goes its merry way. So that reaction means we can count the total number of neutrinos coming from the sun, independent of whether there was an electron type, which is what's made in the sun, or muon or tau, right? And that's what made snow so unique as an experiment. So our job was, okay, somebody's counting electrons and someone is counting neutrons, and we compare those results. So what did we find? This is what I showed you before, where every other experiment before snow saw that the number they measured was lower than the number expected. And when we get to snow, well, it's the same thing. But here, I'm only counting the first channel, electron neutrinos. So what this tells us is the number of electron neutrinos coming from the sun does not agree with the prediction. However, if we then add all of the other neutrinos, the mu and the tau, and compare, so this is the total, you see that within errors, it agrees spectacularly well with the model. So what's happening here is that neutrinos that were made in the sun as electron neutrinos, as they traveled to the Earth, they changed into a different type of neutrino that the other experiments couldn't see, and that we could not see with this channel alone. That's the number of electron neutrinos. This is the other one. So 1/3 of them persisted as electron neutrinos. The rest were converted into other types of neutrinos. So this is what we call oscillations, and I'll get more into that shortly. But the neutrinos change their flavor as they travel. That's the crux of it. Okay, so now you started with these. Half or 2/3 of them changed to another type of neutrinos that were blind, the other detectors were blind to. We saw the normal ones here, and we saw all of them with the second reaction. And so that proved that neutrinos are changing their flavor, they're oscillating as they travel through the sun and onto the Earth. So that was completely new physics. It doesn't fit in the standard model at all. Okay, so this is an analogy I like to use sometimes, totally fake. But anyway, imagine, an apple tree falls off, or an apple falls off an apple tree. When it lands on the ground, it's a banana. You'd be surprised, right? And we were. So this decades-old puzzle about neutrinos has been solved. Okay, so we know they oscillate. What does that actually mean? Well, it means somebody goes to Stockholm. This is Art getting his Nobel Prize, much deserved. But it also means that with neutrino oscillations, and I'll get into this a bit more, if it oscillates, it means the neutrino has to have a mass. It can't oscillate without having a mass. And until then, it was thought that neutrinos have zero mass, and there's no way within the standard model of easily creating a mass for neutrinos. So we don't know what the mass is. We know they have something. We don't know what it is, and we don't know how it was generated. Okay. I don't want to get into this slide too much because it's a little bit over the head, but the problem is with oscillations is that the neutrinos that we see as a particular flavor are actually not the fundamental, if you like, neutrinos that when they're traveling. And so there are what we call the mass states. And each neutrino is some mixture of these U1, U2, and U3. And U1, U2, and U3 you can think of as the physical states. But when they interact through their flavor, which is some combination of those things. And because the mass states, the masses are all different, we know that, then we know those are propagating slower or faster than one another because of the mass. And so sometime later, you could have a different mixture. And if you have a different mixture, maybe you're no longer an electron neutrino anymore, but you're a mu neutrino or a tau neutrino, and it's all probabilistic. It's a wave function, so it's a certain probability that you'll be an electron, muon, or tau, and that will change as a function of time because these wave functions are propagating at different speeds. Now, I wrote this down, A1, A2, A3, just some random variables. In fact, for physics reasons, to access what's really happening, there are 6 parameters. 3 that kind of describe how that mixing is, how much of each is content in each. Those are the thetas. The difference in the masses between these mass states here. And then something called CP. So this is a phase. What it's trying to describe is if you have an antiparticle and you compare it with a particle, Are there subtle differences in the physics between them? And that might be described through this CP violation. Okay. Now, what do we know? What we know is that most of them, ignore these, they've all been measured. They should be measured more accurately, but they've all been measured. We have a pretty good idea with those. But there's one parameter here where we have a value, but we don't know if it's positive and we don't know if it's negative. That means we don't know if M3 is the lightest neutrino or the heaviest neutrino, because we don't know the sign of that thing. And this is really important for a number of theories to understand what the ordering of these neutrinos is. And this thing that I mentioned called CP, if it is 0, then we're in trouble because we don't have anything left to scratching our head. How do we explain the matter-antimatter asymmetry in the universe? We need this thing to be greater than 0. Well, I should say not 0. That's not quite right. It should be non-zero. But we don't know that. There are hints that it's non-zero. In fact, fairly strong hints as time goes on. But it's not ruled out yet at this point. And so there are experiments that I will show you that are looking to try and measure the value of this phase accurately. So we need more experiments. Okay, so I put this slide together. I'm not going to go through a lot of detail, but at the time that Snow and Super Kamiokande, and by the way, Super Kamiokande is another experiment that was in Japan doing similar things. They were looking at neutrinos in the atmosphere as well as solar neutrinos. And we both published around the same time. In fact, Super Kamiokande published first and Snow published later. Snow's was related to the solar neutrino, so it's a solution. But both experiments discovered neutrino oscillations, and that's why there were 2 co-winners of the Nobel Prize. There were basically 4 experiments running at that time, and they were the ones who discovered this neutrino problem. This one, Homestake, I couldn't go all the way back on my graph. That goes back to the 1960s when they started doing that experiment. But that was it. That was the activity in the field. Now, and I'm just going to flip through this. Now, well, another experiment came online, after, similar to Snow, but in Italy. But then people realized, hey, we can study neutrinos by going to a reactor. They make tons of antineutrinos, so let's go park a detector near a reactor. Other people thought, hey, we can make neutrinos at an accelerator, and we can take a beam of neutrinos and shoot them across the Earth. And so there are all these experiments and new ones coming online that you might have heard of. Shooting a beam of neutrinos to understand other properties of neutrinos. There's a strange process, which I'll talk about if we have time, called neutrinoless double beta decay. You think, okay, that's got neutrinos. In fact, that's one of the experiments where we could learn the most about neutrinos because of their absence. And you'll see there's a fair number of people working in this field. And then people are building telescopes where we're looking now at neutrinos coming from outer space, trying to understand these sort of cataclysmic events in the universe. And can we learn something from the neutrino signal as well? And finally, there are experiments. I only put one here because I ran out of room. But the Katrin experiment where they're trying to measure the neutrino mass. So what I'm trying to get you to see on this plot is that from the time that Super K and Snow and this discovery happened, the field has just exploded in terms of activity. And in the previous talk, we heard about working in large collaborations. Most of these collaborations have many hundreds of people involved in them, and they are all international in nature. The experiments are so big and complex that you simply can't do it at a university within a home lab. You need that larger international community and literally hundreds of people and lots of funding agencies to create these detectors. But it's just been an explosion. Okay, so I'll get into my case studies here. So I have, and just so you don't get too worried, up here is the emergency stop. If I start running on too long, I push that button and we jump to the conclusions. So I'm going to start with the neutrino mass, because in many ways, that's one of the most fundamental ones. So we know it's non-zero, but we also know it's incredibly small mass. And the way this works is by using tritium decay. So tritium just undergoes the standard beta decay. So a neutron turns into a proton, kicks out an electron and a neutrino. So that's the process. But the kinematics are simple. You can calculate that almost exactly 16.8 keV, that's a unit of energy. They share that. But you can imagine if the electron took almost all of that energy, then of course the neutrino has very little. In fact, it even goes to zero. It can't quite go to zero though, if it has a mass, because E equals mc squared, there's energy due to its rest mass. So your job is to try and measure the electron energy spectrum when it's got almost all the energy, right? And so that's what Katrin does. So, the electrons can have any kind of energy up to the 18, but now we're interested in zooming in at the end. Now we're in electron volts rather than keV. So this is expanded by a factor of 1,000. And what you're interested in is measuring what the shape looks like way down there at the tip of this thing. Incredibly hard experiment. Okay. We know, and I think I missed it on the previous slide, that right now Katrin has a limit, which is about 0.45 EV. Did I really miss that? Yeah, here it is, 0.45. I tried to write it in other units. I don't know that I counted all the zeros right when I wrote it down in kilograms. And as I said, 1,000,000 times lighter than an electron. So it is really, really tiny, but not zero. Okay, so this is what the experiment looks like. You take tritium here, and it produces these electrons, and you focus them with a beamline, and you send them down towards your detector, which is at the end here. Okay, doesn't sound hard, except there are so many of them, it's a real problem. So in fact, they do a very clever thing. They build a big electric field in here that stops almost all the electrons. Only the few at the very highest energies get through and make it to the detector, so that they're not inundated with billions and billions of electrons, which they're not interested in. That's very clever. The other thing is, it was a difficult thing to get this thing here. It was built here in Deggendorf, and their geography wasn't very good. This is the route they took to get over here to Karlsruhe. Anybody have an idea why they took such an odd route? Bridges, yeah, because the thing was really big. This is the Katrin detector going through a small, probably French town. I'm not sure, somewhere along the route. They had to go by land at some point, and they had to wiggle this thing through all these houses and whatnot along the way. Enormous experiment, very challenging, and it's now on and it's running, and that 0.45 was the best result ever, but they're continuing on with that experiment. So stay tuned, we might hear more from this. Now, in terms of, this is using energy, well, using accelerators to create beams that you then shoot through the Earth. Okay, so an example that I picked in Japan, there's an accelerator called JPark, and it produces a beam of neutrinos, and it just goes 295 kilometers to a detector, which is under a mountain on the opposite side of Japan. So an accelerator works by accelerating here protons up to a very high energy, then they smash it into a target, and that just boils out tons of particles, including lots of muons. And those muons, though they're charged, so with electric and magnetic fields, you can focus them. So now the muons are kind of all pointed at your target. Eventually they decay, and when they decay, they produce neutrinos, in this case, muon neutrinos. And those muon neutrinos are now roughly pointed at your detector on the other side of the country. And so that's what they do. The sensitivity, so you can ask, what is this probability that something oscillates? It has this complicated formula, but what you need to see is there's two key, all these things are fixed. There's a length, how far away it is, and the energy. So you pick your energy of your accelerator and where you put your detector, so that this probability is as small, well, as large or small as possible. We want the muons to change into electron neutrinos, so we want that probability to be high. And the next plot kind of shows that. So they're here at 600, which is kind of where this peak in the spectrum is. So that's where they've situated themselves. That's 295 kilometers. And with this, what do they learn? Well, these curves are all for different assumptions about what that CP phase would be. So if they measure up here, then it tells us it's -1/2 pi for the phase. It's an angle. Whereas if they measure down here, then it will be the other direction, +1/2. What we want to avoid is that it's not 0 or pi, because then there would be no CP violation, right? So we don't want it to be on the black curve here. But it's a very difficult measurement. You know, the number of neutrinos is still not huge. Over many years, they'll integrate some thousands of neutrinos, okay? But they have a chance of measuring what the CP is. And not only that, there's dashed and dotted lines here. We'll get to this in a minute when I talk about neutrinos double beta decay. And when I said, if we don't know whether M3 is the lightest or the heaviest, different result. And so you might be able to get out some of the mass ordering as well from these experiments. Okay, so this experiment is under construction. I mean, they have run this accelerator already at a smaller detector. This is the new detector, 260,000 tons. It's just huge. It's the size of a football field. I was there about 2 months ago, and they actually have a ramp that goes to the bottom. You drive into their detector in a bus, okay? It's absolutely huge. And then they have 20,000 light sensors all around the outside to look for the flash of light that will be created when a neutrino interacts in the target. And this was actually previous trip, but this is, you get a sense of scale. Here are some people standing at the bottom of what is now, and so they're now building this as a tank to hold the water. This is just rock at the moment, but they're building a stainless steel vessel that will cover that entire thing, and it's probably pretty close to finished now, based on how the progress they were making at the time. So this experiment is moving incredibly quickly. There will be new results in the very near future. I'm sure of that, and this is going to be, again, world-leading results that are going to be very exciting. There is another experiment, and I know some people here are probably working on that. It's called DUNE. It's it's even more ambitious. It's a little bit, you know, it's going to be probably more like 2031 before they turn on. But these are very complementary experiments. In this case, near Chicago, Fermilab, you send a beam. Now it's 1,300 kilometers because the energy is different, to a detector in South Dakota. And that's under construction now as well. Okay, mass ordering. Again, as I mentioned, we don't know whether M3 is the lightest or the heaviest. So one way to address this is build a new detector and put it really close to a very powerful reactor, which is just spewing out neutrinos in all directions, but some of which will hit the Juno detector. And so they're trying to address this problem. We know M2 is larger than M1, so we know that ordering, but we don't know whether 3 is way down here and the lightest, or way above those and up here. And we don't know the absolute value of any of these masses. Okay, so this is really critical to understand how neutrinos get a mass. Neutrinos 1,000,000 times lighter than anything else. Why is that? So understanding this may give us a clue to understand why they are so light. And then it's a key ingredient, as I'll show you in a minute, that goes into calculating this matter-antimatter asymmetry in the universe. But it's, again, not easy. But the Juno detector turned on in August, and we'll probably have to wait a couple of years till we get enough statistics. Why enough statistics? This is what the plot looks like that you're trying to discern. There are 2 curves here. It's almost hard to tell. You want to know which curve you're on. So, you know, you've got to be able to differentiate between the black curve, which is normal, and the gray curve, which is the inverted, we call, when M3 would be the lightest. So they've got to make a precision experiment to actually measure these things. Now, the nice thing about a reactor is the neutrinos have a lot of different energies. So if you can measure the energies and plot the rate as a function of energy, you'll actually map out this shape. And then your job is to say, with confidence, I know I'm on the black curve, not on the gray curve, right? So you need a lot of statistics to do that. Neutrinos are still hard to capture, so you need a huge detector and as many neutrinos as you can possibly get. Okay, and this is the detector under construction. I don't know if these guys are tied on or tied off or not so they don't fall, but they are putting the photomultipliers around the detector at this point. It's now all been finished. They've turned on the experiment. After 1 week of data, they were already publishing calibration results. It's a phenomenal success story. This is Jinping in China. Okay, so it's again, hold your breath. That data is coming soon. In terms of neutrinos double beta decay, I said that's a little odd. How do we probe the nature of neutrinos with something that has no neutrinos? Well, it goes back to normal beta decay. We've seen this a couple times now. Neutron decays to a proton and an electron kicks out a neutrino. That's normal beta decay. And you might be familiar with that, for example, carbon dating. A lot of people have heard of carbon dating. That's exactly what's happening. One of these neutrons is converting into a proton. Now it's nitrogen, and it kicks out an electron, an antineutrino, and we count how often that happens and tells us how much carbon-14 was in there. Now, it turns out sometimes in a nucleus, even though it's got lower energy states it could decay to, it's not allowed for single beta decay. You'd have to actually add energy. And so that doesn't happen. But, and I told you this is really rare, but if simultaneously 2 neutrons both do a beta decay at the same time, so now I took rare and it's rare squared, so it's really, really rare. But that has been seen. This is a process that doesn't violate anything. You would expect it to happen. You just expect it to happen rarely. And indeed, the half-life is about 10 to the 21 years. So that's 150 billion times longer than the age of the universe. Fortunately, Avogadro's number is big. So if you have a lot of atoms, there's some probability that some will decay, and that's what you see. And that's been measured. I actually feel sorry for the people who measured it, because after 20 years of hard work and finally measuring that, nobody cared because they were more interested in this process, which is the exciting one. This one is neutrinoless double beta decay. So it looks exactly like this one. You're kicking out an electron and neutrinos twice at the same time. But something funky is happening here. My neutrinos don't get out. That's why it's neutrinoless double beta decay. It's never been seen yet. It violates a lot of things that we hold dear, like lepton number conservation and so on. And if it does happen with what we know now, the lifetime is, another 10 to the 7 longer than this one. So it's going to be a really tough experiment, but it's really important because of what we would learn. And what do we learn is, if you ask what's happening here, there's a theory. Every particle I told you has an antiparticle, but because the neutrino has no charge, maybe the antiparticle is the same as the particle. And if that were true, then an antiparticle here, you can think of it as annihilating with the other neutrino in the same reaction. So there's two antineutrinos here. But if in fact antineutrinos and neutrinos are the same thing, then one way of thinking about this is that they can annihilate on one another, right? The other way you can think about it is the antineutrino is emitted here, and that's like going backwards in time, accepting that antineutrino as a neutrino here. But either way, the idea is that the neutrinos disappear and don't come out of the interaction. And if that happens, that's so-called Majorana-type neutrinos, if that happens, then it has a really fundamental impact. It could help us understand this matter-antimatter asymmetry in the universe, where, as I say, we've got 10 billion and 1 of this and 10 billion only of that. And you're left over with 1. The rest has gone into energy that's powering the universe. And that, 1 in a billion is what's left over. That's what we see when we look up in the sky. And it could also, this mechanism, so there's a theory here on how to invent masses for the neutrinos. It requires a Majorana neutrino, most likely. And so if this is correct and you see it, then we learn a lot of things. Not only that, but the rate, I said it's about 10 to the 28 years. The rate depends on the mass of the neutrinos. And so we learn something about the mass of the neutrinos as well. Okay, so that's why these are exciting things. And there are detectors all around the world. I'm going to speed up, so I won't go into the detail here. But there are experiments all around the world that are trying to measure this. They're all the same sort of thing. You have to have your isotope be one of those ones that does double beta decay, not single beta decay. And you have to make them extremely big. So this would be 60 tons of liquid argon. The annual production worldwide of xenon is about 50 tons per year. So to build this detector, you have to take all of the xenon that's produced worldwide. And so it will take decades to accumulate the xenon, to build it and operate. So these are big, challenging experiments. And, you know, if you just have one little piece of radioactivity that tricks you into thinking you saw it, you're ruined. So all of these things have to worry about backgrounds and major international collaborations. And okay, I'm not going to go through this, but this is the idea. Those two electrons coming out produce light. You have photomultipliers down here. They say, yeah, I saw the light. You put it in an electric field. These electrons drift up and they create a signal at the top. So now I know where and from the time it takes, I know how far it went. So now I know where in position that thing happened, and that helps me identify potential backgrounds. And now it's a counting job and energy resolution. You measure the energy of those electrons very exquisitely. And that experiment that I showed you, we're hoping will come to Canada. That's XLZD. Yeah, but you'll see there's big experiments in Japan, another one already almost in operation with tellurium in Canada, some in Italy, some in Spain, and so on. So it's a big international enterprise, all looking at this incredibly rare process and hoping to see it for the first time. Okay, we might get through all of these. So the next one I wanted to talk about is messenger neutrinos. So here the idea is that neutrinos basically come to us straight, unperturbed, because they don't interact with anything. There's no magnetic, they don't bend in the magnetic fields or anything like that. A normal proton coming through has all the intergalactic and galactic, magnetic fields. We have no idea when it hits us where it came from, but neutrinos we do. And light often hits in the atmosphere, photons, and creates these enormous showers and so on. So neutrinos are a spectacular tool. If only they weren't so difficult to observe. And so typically, for these things, you need a very large detector. And so people are building detectors 2 kilometers underwater or under ice. And the size is about 1 kilometer in each dimension. So think of a cubic kilometer as your detector. So obviously, you're not going to fill that with scintillator or something like that. So you use the water or the ice as your medium that creates the signal as well. And there's hopes that you might actually see something coincident with, say, a gravitational wave or something that helps us learn more about the sources. So these experiments are really trying to understand what's happening at that source that's creating these neutrinos. And there are several efforts underway. The longest one is IceCube, meaning in terms of duration in years. So what they have done is they drill a hole down 2 kilometers to the bottom of the ice at the South Pole, which are at the South Pole station. And then, of course, the ice freezes in again very quickly, but your detector is in there, and your detector is just light sensors all the way along. So you're looking for something interacts in the ice, produces this flash, and you detect it. You want that. And it's deep in part to get away from radioactivity at the surface, but also the ice at such high pressure is very pure and the light travels a long way in the ice. Or if you don't like your holidays to be at the South Pole, you can go to the Mediterranean, and there's a detector which is 2 kilometers underwater in the Mediterranean. It's very important to have different latitudes because the one at the South Pole actually only sees the northern sky. And that's because there's too much radiation coming down from the sky into the detector, so coming upwards from the south. But the neutrinos that go right through the Earth, they don't care about the Earth. And so this experiment studies the north sky, and this one studies more of the south sky. So they're very complementary. And just as a little advertisement, there's a new experiment planned for the Pacific Ocean off Vancouver Island. They have built their first real string and will be deploying it in July. So I'd be able to say, it's definitely under construction. In the first round, they will just build about 5 or 6 strings just to see how it all works. But the goal is to get something like these ones where you have close to 100 strings by the end of it. And so the way it works is the particle, if a neutrino comes in and hits something, then it could knock off an electron or it can produce muons or taus. And so you get a track of charged particles going through the water or the ice. And in fact, they're going faster than the speed of light in water or ice. So they produce something called Cherenkov light. And so all those photomultipliers that you sunk in the water or the ice detect that. And you'll measure a track. And you could guess, if I saw this track, I could guess, yeah, it's coming from somewhere over there. And the accuracy of these things is to a fraction of a degree that they can tell where these things are coming from. So very exciting as well, but again, a big investment of effort all around the world to build these telescopes. And these are the sorts of things people are looking for. Some wouldn't have been so obvious, but active galactic nuclei, they have these huge jets, which include neutrinos, black holes stripping a star apart, supernovas. Now, supernovas are very low energy, so they would basically just see an increase in noise when a supernova went off. But it's very obvious, suddenly it's, and then poof, big pulse of neutrinos come through over about a time span of 15 seconds. And so even dark matter you can explore, because if dark matter gravitationally collects and gets bound inside the sun, then the annihilation probability goes up, and maybe 2 dark matter particles annihilate and send out neutrinos, which you can then see with this vector. Okay, I think I have time for one last topic. It's a short one. And this one is just to give you a different flavor of other things you can do. So this is radiogenic heating of the Earth. We have no idea where the energy in the Earth comes from. So we know there's about 47 terawatts total coming out of the Earth. So this is coming from the inside out. The sun dominates completely, 173,000 compared to 47. But the sun doesn't penetrate more than a couple meters into the surface. So this is divided into primordial heat. So that's the heat left over from when the Earth was formed, this hot molten ball. But probably at least half, or maybe considerably almost all of it, 41 out of 47, is coming from radioactivity. Where you have radioactivity, you have neutrinos. And so the idea is all rock, everything. You guys are full of radioactivity. Everybody has uranium, and when uranium follows its complex path and eventually ends up at lead, and it's been there forever, right? The half-life is 4 billion years, so the age of the Earth. But when it does that, okay, it produces new products, it produces a bunch of alphas, but it also produces electrons and neutrinos. And neutrinos is what we can see, so we are able to count and tell the geologists how much uranium there is in the Earth, and maybe even, because there is some directionality, it may be even roughly, is it in the crust, is it in the mantle, is it in the core? That's harder. And then, of course, all of this releases energy, and that's what's heating the Earth. And so this is an example from snow where they have actually measured it so far. This pink and this purple are 2 geoneutrino signals, one from uranium, one from thorium. Okay, it's obviously very complicated in Canada because our detector is close to reactors, which also produce antineutrinos. So that's an interference and all backgrounds. But the field is making progress in being able to see these neutrinos coming from the Earth. Why is it important? Well, this convection, it drives convection. And this convection is what plays into how the crust and all the tectonic plates move. And so you understand tectonic motion if you can understand that convection, which means, can I understand where the heat is? And likewise, the core as a dynamo creating the magnetic field, which protects us from the cosmic rays. We can understand that better. So that's why geologists are interested in this. And I just point out, the deepest borehole ever made is 12 kilometers deep out of 6,000 kilometers, right? And it took 19 years to drill. And when they drilled it, nothing was the way they thought it would be. So there's a lot to be explored in here. And that's why geologists are interested. Okay. So these are my conclusions that I hope that I've convinced you that there's this amazing world. I don't know, this one has gone off. I can't even see that anymore. But my goal was to just introduce you to neutrinos and how functional they are in understanding the world we're in and the world outside of the Earth in terms of what all these weird and wonderful things are. We're making progress on nailing down the remaining parameters which define the properties of neutrinos. But this discovery really led to an explosion of activity, which has consumed a lot of effort all around the world and a lot of collaboration. So I'll stop there. Thank you. Friendly questions.
Thank you for the talk. Very interesting. So I'm curious about like the first one you showed about like the neutrino from the sun to the Earth, and you still have your happen for a second channel that's like including neutrino oscillations and that. So my question is like if the neutrino travels so fast, so like from sun to the Earth it takes about 8 minutes, but their proper time is probably a fraction of seconds. So does that mean that the neutrino oscillations have their capacity?
So the neutrino oscillation follows that formula where I said L over E. And in this case, L is huge. So this is part of the answer, that they will oscillate continuously. And so by the time they get to the Earth, we really imagine that they're just going to be a mixture of the 3 different types. And it's not like we're going to be lucky and be sitting on some peak or trough in terms of the oscillation profile. The other thing I didn't talk about, which is very important, is there is a subtle other effect. The sun is full of electrons, and electron neutrinos can feel that those electrons are there. So there's another so-called matter effect, which actually drives this oscillation as well, which I didn't talk about, but it's critical to understand it. But yeah, we feel it's just a homogeneous mixture by the time it gets to the Earth, and our numbers are pretty close to 1 out of 3.
Thank you for the talk. So I'm curious that there's this PX with the delta PX in the imbalance. You know what I'm talking about?
No.
Okay. You were saying you might measure that there is an asymmetry between the anti.
Right.
Okay. Right. So if you do measure that, how does that help you tell a story of like why there's more matter?
Well, it's all heavily interconnected. So basically, if there's a matter and an antimatter asymmetry, more of one than the other, and yet you think you started with equal amounts, there must have been something happening at the beginning of the universe that meant neutrino or antiparticles behave different than particles, right? And CP violation, if it's there, is a possible mechanism. So we don't know this right. We might have CP violation, it still doesn't explain, but we need to have something that creates an asymmetry, and that's what CP does. It says antiparticles and particles don't behave exactly right, and so then you could imagine a process which maybe in some decay process was creating particles more than it was creating antiparticles. So it's kind of a necessary ingredient that we see CP violation, but it's not the full story. We still have to understand how these things got mass and so on, and what the right model for neutrinos is to be able to follow that up and come up with a real answer to what's happening.
But it's possible that
It's possible that the delta CP is 0. And if it is, then that explanation can't work. But I have to say I'm comforted by there are hints in the data, not enough to put your hand on your heart yet, but there are hints that suggest it's non-zero and in fact fairly maximal.
Neutrinos reaction, do you expect them to trigger photons or become dark energy and violate conservation of energy?
No, they don't violate conservation of. So the question was about in the neutrinos double beta decay, where you have these 2 neutrinos kind of annihilating on each other, what's happening there? They don't violate energy because it all happens within a system, and the system absorbs that problem, if you like, right? And so any energy that they might have taken away is now given up to the electrons, something like that. So there's no conservation of energy. The way I like to think of it sometimes is that you would have no problem with me shooting out an antineutrino. And if that was absorbed and going into the next vertex and being absorbed, but the problem is I should have an antineutrino coming out, but an antineutrino coming out is exactly the same as a neutrino going in. And so I could, and if an antineutrino and a neutrino are the same, then that process works. And so I can basically have just like a normal vertex in a Feynman diagram where my two neutrinos interact in that way.
So, your talk, you mentioned many possible sources of neutrinos, right? You have the sun, you have power plants, then there's experiments where they create the beam of neutrinos to detect somewhere further away. So with, all of these possible sources of neutrinos, if I have a detector that, say, wants to detect specifically, one type of source, say it's the sun, or it wants to detect the closest nuclear power plant or something like this, how can it kind of ignore everything else in especially since neutrinos?
Yeah, so the one you can't get away from is the sun. I mean, that's the 10 billion per second going through your thumb, and it's everywhere. So you can never avoid those. But those neutrinos, you wouldn't have picked up on it, but when I showed the energy spectrum from the sun, that ends at about 20 mega electron volts. That's very low energy. The ones that are coming from the cosmos and stuff, we're talking about TeV or PeV. They're huge, vastly different in terms of the energy. If you want to study reactor neutrinos, your only hope is go put your detector beside the reactor neutrino, and there the flux now is enough that you'd be able to see them. And in that case, it's an antineutrino. In the sun's case, it's a neutrino. And it turns out when an antineutrino stops in the detector, then it's an inverse beta decay, and it will actually kick out a neutron rather than the other way around. Beta decay was a neutron going to a proton plus an electron and an antineutrino. In this case, it'll kick out a neutron. That neutron will wander around in your detector and eventually capture, and when it captures, it will produce another flash of light. So if you're buying a reactor, the signal is quite different because first you see the initial thing, and then some milliseconds, which is a long time in our field, later the neutron captures and gives a second. That will never happen for a solar neutrino. So you get these additional handles that allow you to discern what's happening. Yeah, so that's a little bit hard thing to grasp, but so what's thought? Okay, so the question was, what might be the mechanism that produces mass for neutrinos? And one of the intriguing ideas is that the neutrinos are the only particle, so it's left-handed. There is no right-handed component to the neutrino. And that's unlike all the other particles. The Higgs mechanism relies on that exchange between right and left. So that doesn't work for neutrinos. So you can't have a neutrino mass coming from the Higgs mechanism, at least in my understanding of sort of the naive models of the Higgs. So instead, you have to create a different mechanism. One idea is that there's sort of this imbalance where there are actually right-handed neutrinos made through something called the seesaw mechanism you might have heard about, but they will be incredibly massive neutrinos. And so we don't see them easily. And then the neutrinos consequently are driven the other direction and are very light. And that might be a sterile neutrino, which might be another neutrino type, which might explain dark matter and so on. So there's all kinds of intriguing topics in there, but that's the fundamental idea, that it can't be Higgs because it's only a left-handed particle.
Yeah. Of all the upcoming experiments that you've identified, is there one that will be particularly sensitive to distinguishing between successive theories and the standard model people must be proposing?
Well, a lot of them Will not. Oh, so the question was, of all the different things I showed, you know, which ones of those might be successful at the successor model to the standard model? So really finding new physics. The one that really strikes me is the neutrino-less double beta decay. Because in that case, first of all, the neutrinos have to be Majorana. That's maybe not built into the standard model because we don't know if they're Dirac or Majorana. But we're eliminating two neutrinos, which both have lepton number. So lepton number universality would have to be violated in order for that to happen. So, you know, that's completely outside the standard model.
Okay, I think we have to stop here. Let's thank Tony again for
Thank you.
next one. So though I don't think I was tasked with this, let me just then invite everyone to come to a reception. It's in McLennan Physics room 125. Oh, Youngbeck, I'm sorry.
No, you are right. You have not been tasked.
Okay, so I'll be brief here. So my name is Youngbaek Kim. I'm a professor in the Department of Physics, and I'm the chair of the Welsh Lecture Committee. And I came here to deliver some thank you messages. You know, this event was organized by a lot of effort from different people. So first of all, I'd like to thank the Welsh Lecture Committee members, Dick Peltier, Sarah Raucher, Pekka Sinervo, Jiching Hong, Dwight Miller. And also, I'd like to thank Pekka and Sid for hosting the Welsh Lecture speakers, and the Sarah Raucher and the Miriam Diamond chairing tomorrow's colloquium. And also, I'd like to thank Helen Ayer, who did also heavy lifting. And we also have some help from other administrators like Harry Murphy and Chunyu Diao. And also, we also have help from our technical staff like Eva Chung and Lilian Lim. So I'd like to thank all of these people. And of course, our big thanks should go to our Welsh lecture speakers. And we have some small gift to give you. So Professor Noble and Professor Pick, could you come to the podium?